Welcome to Computer Graphics. This semester, for this first pre-recorded lecture, we're going to be looking at a simple introduction to what we're going to be doing along the course and an introduction into the idea of real-time graphics, which is what we're going to be working with. To start with the grading of the course itself, we have here two equally valued elements. On the one hand, we have practical assignments, which are testing our skills at the practical part of the course, at the programming and using OpenGL or using a graphics engine as an end user in order to render a scene or make an animation or make a real-time computer graphics program. And on the other hand, we have the final exam, which will be testing our skill at the theoretical part, where we're going to be learning about the calculations, the mathematics and algorithms behind the graphics engine or the rendering pipeline. And we're going to be going in depth into exactly how the computer takes the data that we send it from a 3D world and renders the final image onto the screen. For the assignments, we'll have a few hand-in assignments along with just practical exercises, where each exercise and assignment is testing a specific part or a specific skill, specific usage of a specific part of the graphics engine. But in the end, we'll have the free programming assignment. And in this assignment, we should have a lot of freedom to decide exactly what kind of graphics program we're going to make, whether it's going to be a computer game or simulation where you want the user to interact with what's happening and affect what's happening constantly, where you'll have to program logic and program boundaries to your world to make sure that the user can't go outside kind of the boundaries of your design. And on the other hand, you could do a completely non-interactive animation, where every time that your program is run, the animation should go through its progression in the exactly same way. In that case, you'd have to take into consideration time management, so that on a fast computer and a slow computer, the animation would still run in exactly the same way on both, so the experience for the end user would be the same. Or possibly a mix of both, an animation with some degree of control over where the camera is looking or what's happening, or a computer game where there's logic and decision making by the user, but progression of the game is shown in pre-decided animations. So this slide is simply a list of things that computer graphics are used for. It could be a lot longer, but the interesting thing to look at here is probably the difference between pre-rendered animations and real-time computer graphics. So looking at pre-rendered animations, this would be something like any three-dimensional animated motion picture that you've seen, and the bulk of the calculation behind this type of rendering will usually be done through ray tracing. And when you set up a ray trace, what you do is you take the viewport or the screen that it's meant to be viewed on, and you take its resolution, the resolution that the film is supposed to be in, which in high definition would be 1920 by 1080. And for this resolution, you take each and every pixel, and out of each pixel you imagine that you're shooting a ray in a specific direction. So for a pixel in the middle of the screen, this ray would be shot into the center of the scene, straight forward from the camera, but along the edges or top and bottom it would be directed more to the left or right or up and down. And once you've decided on the direction of the ray for each pixel, you follow that ray into the scene. You see which objects it hits, what color these objects are and how light affects these objects. If these objects are reflective or if they're transparent, you may have to follow the ray onward further into the scene. Do a lot of calculations. There may be things like fog and different diffuse and different effects that you have to take into consideration. But in the end, for each pixel, you end up with a color, which might be a summarization of different colors of different elements that it hits along the way. And this color will be the color for that pixel. Then you move on to the next pixel, shoot a ray in its direction, and go through the scene in the same way. Calculations like this are really costly, and so in order to render just a single static frame in this way, it can take several seconds or even minutes, even for a fast computer, to render a single frame. Meaning that in order to render an animation, where you have to render 24 or more frames per second for several minutes or even a full feature length, hour and a half, it can take weeks or even months for the computers just to render the scene, even after the whole film has been designed and directed and done. So this obviously is not something that we can easily use for interactive graphics programs like computer games. So instead, what we're going to be looking at is real-time computer graphics, where the images or the static frames are compiled and rendered on the fly as they are being viewed, as the program is running. In this way, a user can interact with the program, can change the direction of the camera or change what happens in the scene, and see the effect of his decisions instantly. And obviously, for computer games, this is an essential thing to be able to do. And so we need a different type of rendering machine than ray tracing offers us. But even so, when rendering a single frame, we need to do several things. We obviously need to place a camera somewhere, set a camera type, set up a viewport. This will typically be done once for the scene or for each frame. Then we need to set up the colors of the materials that we're working with. Different parts of different objects have different materials, different colors. We have to set up lights that will affect these colors. We manipulate our coordinate frame in order to position and orientate these different objects in our scene. We set up texture images to be projected onto these objects, and so on and so forth. And then we draw the primitives. And when we draw the primitives, or the triangles in OpenGL, basically the basic geometrical elements that all of our objects are made up from. When we draw these, we have to take into consideration all of these things, these colors, these lights, where the camera is, so on and so forth. And all of this needs to be taken into consideration and calculated for each frame. So a simple scene for which we're going to render a single frame can consist of hundreds of thousands of primitives of these base elements. And in order to do an animation, we must be able to run at something like 24 or more frames per second, meaning we have to render 24 frames where each frame will be doing all of these different things for up to 100,000 or more primitives. And we have to do it in less than 40 milliseconds in order to have time to render the next frame and the frame after that, and 24 frames for each second. Preferably, we'd like to do this between 10 and 20 milliseconds, because this is the smooth rendering time that we're looking for, especially in competitive gaming. And also because a computer game will have to do more than only the graphics, so we have to take into consideration that it will be calculating paths and decisions for non-player controlled characters. It'll be calculating physics, it'll be calculating all the boundaries of the game, making sure everything runs smooth. And so within these 40 milliseconds or less, all of these things need to be able to happen along with the graphics in order to get an animation that will affect the user as a smooth animation rather than simply a series of static frames. So in order to get all of this done in this short amount of time, we introduce the rendering pipeline, which is our machine or our engine that we're going to be using to render the graphics. This is the machine that the graphics, or the base elements of the graphics that we send through, the primitives, will go through. they'll go through different calculations here, which the boxes represent. For instance, going through the model view matrix where the position and orientation of the object is calculated. After that, doing lighting calculations for all of the vertices. After that, going through the projection phase or the projection matrix, which takes our three-dimensional image and flattens it out, projects it onto our imagined two-dimensional screen. After that, clipping everything that may end up outside of the box or the viewport that we want it to be on, and then going on to rendering all of the pixels specifically in order to fill in all the areas with correct colors. So obviously a lot of calculations have to happen here, but the difference between this machine and the ray tracing is that rather than taking each and every pixel and taking the entire model into account for every pixel, we're gonna run through this engine for each primitive or for each vertex, meaning that the calculations will never be more costly than some specific amount per vertex or per triangle that we send through the engine. So we'll have a look at the OpenGL pipeline very frequently throughout the course, seeing as that's the main engine that we're going to be looking at. We're going to be focusing on specific parts of the engine, specific calculations, specific algorithms that make it up. And in the end, we'll kind of have filled in all the boxes, filled the spaces between them with calculations. So we'll be able to imagine the route of a single vertex or a single triangle throughout the entire engine, where it will end up, which colors it will have, and how the space will be filled up with actual pixels in the final rasterized image. To begin with, though, we're going to go back to the basics, back to a little bit of basic vector mathematics, which we're going to build the rest of the calculations on, and that'll be the subject of our next lecture.